normal gene fusions here, right? And we have selected like 10 or 20 examples and using their raw sequence data to use the existing algorithms or just using some command line graph to get the raw sequencing to get the evidence of the raw sequence, the raw read sequences in this data. But definitely we cannot to perform very comprehensive validation of all those results we cannot do.
Question. When you say you detected about 93% of the previously annotated ones, two questions. One is, how many are those occurrences? Is it about 200 or is it about 1 million?
10,000.
10,000.
Around 10,000. Yeah.
A great number then. And what happened to the other 70%?
Well, yeah. So right. That's a very good question. So I would say, so the problem, so the missing gene fusions, the missing things could come from two sources. The first one is in our KMA kit, we require the exact match, but for the algorithms like the MapSci3, they can allow some mismatches, right, between the reference genome and the gene fusion sequence, and the read sequence to detect the gene fusion. Another thing is we actually do not use all those k-mers from this sequence data because there are too much noise in these data sets. We only use the k-mers with at least 3 occurrences in the data set. So we would ignore those gene expressions with those gene fusions with very low expression.
How big is K in your KMA?
We have conducted some experiments using from 18 to 31, and in our previous experiment we found when the K is greater than 19, like 20 or 20 plus, the results are very steady. So we tend to use 20 or 21 in our experiment. And actually, in the human genome, if you use a 20-mer sequence, I think if I remember it correctly, 99.5% of the 20-mers are unique in the human genome. Right? Yeah. 95% or 99.5%. I'm not sure about the exact number. Yeah.
Well, we have plenty of time for more questions. Ask something.
I have one question. So, can you explain the reason for algorithm to claim faster than other? Was there any particular insight of this matching strategy, or?
Yeah, most of the gain of speed comes from the L0 data structure. The L0 data structure. And another thing is, I think it's about how to partition the map. So there are some works to organize the data as a binary tree and using some hashings for each to organize all those data sets in a binary tree, and for each node in this tree they use a hashing function or a Bloom filter to construct to support the query of a k-mer for this. But so because of it is a tree, right? If you want to get a result of presence of k-mer, sometimes you have to go through the whole tree, all those nodes in this tree.
So I think Dr. Hayes, you had asked about the reason for splitting the k-mers frequency. Great. I guess, I don't know if you can talk about it or I can talk about it, but another reason is the compression. That's how we were able to compress the data. So you can think for k-mers with very low frequency, let's just say they occurred in one sample, and we have 1,000 samples. But there's no reason to store that entire 1,000-bit vector in memory because we only need to know which samples it appears in. So we can only store in memory, 1,000th of the memory that we would need. And for different, if we have, maybe a k-mer that occurs in 999 of the samples, we only need to store which sample that k-mer doesn't appear in. So by splitting this into frequency buckets, we can apply different compression strategies to each bucket, and that's why we can compress the data from, terabytes and terabytes down to just a couple hundred of gigs. So that was another reason, aside from quick lookup, for dividing by frequency buckets, was to compress the data.
When you say that you only need about 70 gig, is that in main store or is that all in a file?
In the file.
So how much memory do you actually need to run this?
12, right.
Okay, I see, we're at 12 gig, right.
Okay, so you said that for this to work, you're doing exact matching. And you kind of put out this hypothesis that, maybe we're only getting 93% because we're doing this exact matching. So let's say you want to go for gold. You want to go over 100%. How difficult would it be to extend this to do not exact matching, so some kind of fuzzy matching? Do you have any strategies or do you think that would help you kind of make up this 7%? And do you think it would be, would you see downsides other places? Like, do you think you'd run less efficiently or harder?
Right. That's actually something we can explore, and probably we can try to replace to replace an A with a T, right? And then redo the query and to see how it works, right? That's something we can explore. But in our gene fusion, because we actually so as I just talked about, we only use 21 mers here in this gene fusion, and we only use the 20 bases on each side of this fusion site. That's because only this sequence is unique to this gene fusion. If you want to include the other bases in this query, it will have a lot of noises, right? And for this gene fusion sequence with only 40 base pairs, if you replace one layer with another one, then you have to re-query all those k-mers in this sequence. So it basically it just returns the result of a totally different one, right? It actually depends on where the mismatch comes from, right? So if the mismatch comes from the read sequences, because we actually collect the k-mers, so each base in the reference genome will be covered by multiple reads. So in most cases, we actually can have the correct k-mers. Is that what you mean?
Right. I think, in this scenario, exact or not exact may not be that important because, your maintainers, unless there is a really important mutation right there, in fact, junction.
Right.
It's very rare that schools really have that mismatch. Because even though some reads has a mismatch there, a lot of others may not have it. So
You say there's enough redundancy in the
there's
reading.
yes, there's enough redundancy someone discovers something new in their own patient, like something abnormal, right? They really want to see, okay, is this something, suppose it's something clinically interesting. They really want to see whether in the general cancer population, this can be found, or what are the prognosis or survival related to this particular clinically interesting feature, right? But right now, there's no good approach to do that, to survey the entire, like 10,000 something data sets. You have to go through this very detailed alignment to find that, and which like costs 700 some computing hour, computing days, right?
Right.
So, but this is, you know, one of the first two approach that allow you to do this, and our approach is actually much faster than the other alternatives. But definitely the way that this can be compressed and can be this fast, we're basically exploiting the redundancy in the data and how to organize the data and how to use this very fast hashing structure to put those together. And actually this whole thing is called a tree. I think they didn't talk about it in detail here, but it's really like a B+ tree. However, B+ tree is something you have to search based on the intervals, right? But this one allows you to search based on the categories. It's like you can map anything to a set of categories without really requiring the ordering of it. So I think it's quite neat. Besides this application, there could be a lot of other applications. Yeah. Yeah, okay. Any more questions?
Oh, good. It's always interesting to hear for an entire period then, in some detail, PhD research. So let's have more of those in the future. And for now, thank you very much. Stay tuned.